Alright, so in this video I want to finish the chapter on basic definitions and properties of graphs. So we're gonna start with the graph minors. Right, so I already mentioned these things a little bit in the first video, lecture 0. Right, so we have seen the deletion operation already, right? So deletion, what was deletion? So we write backslash, right? G delete E to denote the graph obtained from G by deleting E. So E is an edge, right? Deleting an edge E, and when you have a vertex V, then this is a graph obtained by deleting V and all edges incident with V. Sometimes we just write G delete X for some set X, which is set of edges, or some set X of vertices. So that is the same as saying, oh, we delete all vertices in set X or all edges in X. So that's a deletion, right? So if we have a house, so this is now, and if I have an edge E, then when I delete it, then we end up with a graph like this. And contraction is a different operations. That is to identify two ends of E as a single vertex. So if you have taken the topology course, you might have seen something like that. And so if you have 2 points and you can identify them, and now from that time you record it as a single point. Yeah, so for instance, in the case of house, if you identify this end of E, then it becomes this. So the number of vertices is reduced by 1 if E is not a roof, and number of edges is reduced by 1. Right, so it's graph obtained by contracting. So we contracting E, that is the that is to first delete E and identify both ends into a single vertex. And if you have parallel edges, things may go weirdly. So let's say if I have something like this. Okay, let's try this. If I contract E, then these two vertices become a single vertex, but everything else stays same. So the incidence relation that we initially had stays same. So that means we're gonna have these two edges, and it's a still loop, and that's it. And what happens with this red edge? That becomes loop, right? So that's contractions. And you can still contract the set of edges at once. So if you have a set of edges, you can contract all at once. That is same as contracting each component into single vertex. Let's see an example. So if I have a graph like, okay, I don't know what I'm gonna draw. Apartment. Okay. Now let me mark some edges. Right? So let's say X is the set of red edges. So what happens if I contract X? Right? And then all the, so this is same as contracting edges one by one, all the red edges one by one. But then these three vertices become one vertex, right? And those five vertices become one vertex. And these two vertices become one vertex, right? So what ends up is a new graph, right? Let's use this color and red. Where's green? Okay, green. All right. Now let's be careful. If I look at this vertex, that's adjacent to 1, 2, 3, 4, 5. I mean, there are 5 edges. Where are those 5 edges going? 1, 2, and it has 2 edges to the green vertex and 1 edge to black. How about this vertex? Right, that vertex has 2 edges to the red vertex, so we have 2 edges to the red and 1 edge to green, and yeah, that's it, right? How about this vertex that has 2 edges to green vertex? How about the edges from this red guy? Well, we have 2 edges going down and 1 edges to the green vertex, right? That's right. Now, how about the vertex on the blue vertex? Well, blue vertex has 2 edges to the green vertex and 1 edge to the right, 1 edge to the left. And this bottom right vertex, this vertex has 1 edge to green vertex. Right. So that's okay, and then these 2 black vertices are adjacent. Right? So let's see how many edges do we... Oh, and one is missing. There's an edge joining 2 green vertices. That becomes a loop. Okay, how do I draw? Okay. Right, how many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that's 19 edges. So initially I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. How many edges did we contract? 1, 2, 3, 4, 5, 6, 7. Oops. So, did I miss some edge? Let's see. Alright, if 1, 2, 3, 4, 5, 6, 7. Oh, actually, that's 8 edges to be contracted. Right? 1, 2, 1, 2, 3, 4, 5, 6. No, it's still 7. Right, 1, 2, 3, 4, 1, 2, 3, 4. Oh, 4 times 3, that's 12 plus 5 times 2, 22, and then 27. Oh yeah, so 27 edges is correct, 7 edges, right? So let's see, 5, 1, 2, 3, 4, 5, that's 5, and 1, 2, 3, 4. So degree of this vertex is correct. How about the right, the 2 edges, 1, 2, and 1, 2, 1. Okay, 1, 2, 1. 1, 2, 3, 4. So did I count correctly? 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh yeah, this was 20 edges. That was correct. Right, so that's how you get a minor. So minor, what is a minor? H is a minor of G if H is equal to H delete X. Okay, H is obtained from G by deleting vertices and edges and contracting edges. So in other words, H is equal to G delete X delete Y, contract G for some set of vertices, set of edges, set of edges, right? Yeah, so that's a minor. Okay, and there's another way of saying some graph is a minor, right? How do we? Yeah. So, well, let me say as an observation. So H is isomorphic to a minor of G if there is a function phi from vertices of H. Okay, let me say defined on the vertex set of H such that phi of V is a connected subgraph of G, and phi of V, so phi of V and phi of W have no common vertex. So if you have for any distinct vertices, right? So the vertices of H are mapped to a connected subgraph of G, and they are mapped to disjoint connected subgraphs. And okay, that's not all actually. I need to define another function. I need. Okay, let me. Yeah. So let me make this function on this vertex set union edge set. So if E is UV in V, so this when I write UV, that means an edge joining UMV. So if an edge joins two vertices U and V of H, then this image is an edge joining a vertex of phi U with a vertex. Yeah, so that's the edge of G, vertex of phi V. And also I want to make sure that E1, E2, whenever we have different edge, then these things are distinct. So this is what's called the H model. So if you remember, if you look at this picture, right, look at this picture, and in the minor, every vertex is corresponding to a vertex or set of connected subgraph in the original graph, right? For instance, if you look at this red vertex, that corresponds to this red subgraph. If you look at this blue vertex, that corresponds to this blue connected subgraph. And the green vertex corresponds to this green connected subgraphs. So this, in the minor model, in an H model, you have a mapping from the minor to the original graph, and all the edges outside of the minor correspond to, outside of this connected subgraph correspond to an edge joining two vertices corresponding to phi u and phi v, right? So that's the, that's another way of describing a minor, right? H is my small pictorial minor of G if there is a function like this. If there is a collection of connected subgraphs satisfying this. And you can assume that actually phi v is a tree instead of a connected graph, because you don't need to have edges inside. Right? You don't have to use all the edges of G. So you can delete edges as long as you keep connectedness, then it's gonna become a tree inside G. All right. Oh, I should say phi v is non-empty connected subgraphs. So, and some people define this as a H minor. Just if you're reading some paper and some people, then this might be the terminology. We say graph G has an H minor if there's a function like this. All right. Now, let's look at the one theorem. Oh, by the way, before doing that, I want to talk about the subdivisions. Right, so if I have an edge, E, and if I subdivide E, then I'm creating a new vertex of degree 2. In the, let me say, middle of E. So all these operations, why do we care about these contractions and subdivisions? And these are the operations that preserves planarity, right? So later on we will characterize planar graphs in terms of minors or subdivisions, and that's why we care about these things. And if you have taken discrete course, again, this must be familiar. All right, and we don't have a notation for that. Some people define notation, but I'm not going to define notations. And we say H is a topological minor of G if a subdivision of H is a subgraph of G. In other words, when you delete some edges and vertices of graph G, you end up with a subdivision of H. Then we say it's topological minor. So for instance, we have a house now, and then I had an apartment, right? Let me just throw in a, oops. Right, so if I look at this red subgraph, that is a subdivision of this house, right? Okay, let me say, subdivision of H. So this G, so H is a topological minor of G. But if H is a topological minor, you can get H as a minor as well, because whenever you have a degree 2 vertex, then you take one of the edges incident with the degree 2 vertex and contract it. Then you can recover the initial graph, right? So that means if H is a topological minor of G, so like this example, right? If H is a topological minor of G, then first you delete all the edges not in these green parts, and whenever you have this degree 2 subdividing vertices, you contract one of the edges, then you end up with H. So this is an easy consequence. If H is a topological minor of G, then H is a minor of G. Now this is easy consequence. How about the converse? Suppose that I have a graph H, which is a minor of G. Now, can I say that this graph is a topological minor? No, actually not. What are the examples? Let's think of this example. And if I contract E, then I have this particular 5 vertex graph. Now, can H be a topological minor of G? No, the other way around. Let's say this is G, this is H, right? H is G, contract E. Now, can H be a topological minor of G? No, because imagine a subdivision of H. Now, the degree of the branch vertices, so these are called the branch vertices. Okay, let me say it this way. When you take a subdivision, these two vertices are initial vertices, so these are called branch vertices, and that's a subdividing vertex. So, for instance, these vertices are branch vertices, and the degree of these vertices doesn't change even if you subdivide the edges. So in particular, there is a vertex of degree 4 here. And no matter how you subdivide edges, the property that this vertex has degree 4, that doesn't change. Now, if you look at G, this graph doesn't have any vertex of degree 4. Every vertex has degree 3. So there is no way that it can contain a subgraph having a vertex of degree 4, because the degree doesn't increase when you take a subgraph. So therefore, the converse is false. Okay. So having a topological minor doesn't guarantee that you have it as a minor. Now, we're going to prove some special case of this converse. Let's say as a theorem, if H is a minor of G and the maximum degree of H is m-3, and let's simplify further, and H is a simple. Okay, let's simplify. How do we simplify? Well, let's say H is simple. Let H be a simple graph. If H is minor of G and H is the maximum degree of H is m-3, then H is a topological minor of G. So what this theorem says that this example is essentially the obstructions. I mean, this example has a vertex of degree 4, and that's the reason why we couldn't get a topological minor, even though it is a minor. But in general, if we have a minor which has a maximum degree at most 3, then it is a topological minor. Why? Why is this the case? So let's consider the minor model, right? So let phi be the H model. Okay, or H minor model. Okay, let me change H minor model. That will be simpler probably. We may assume phi v is a tree for every vertex v, for each vertex v of H, because I only care, right, let me show you the definition here, because I only care whether or not it's a connected subgraph. So whenever you have a cycle, you can delete one edges in the cycle, the remaining is still connected subgraphs. So in the end, you keep removing edges in the cycle. So in the end, what you get is a tree. Now, I think it doesn't, okay. Now, because H has, okay, I can assume one more. We may assume that if phi v has a vertex W of degree 1 in phi v, right? If I have a vertex, so let's say I have, so this is mapped to 3. If I have a vertex of degree 1, why do we keep it? Well, the reason why we keep it is because some of the edges are mapped here. Some of the edges by E is mapped here. Then because otherwise I can delete this black vertex. Then, so let me say there is an edge E incident with V such that phi E is incident with W in G. Why can I assume? Let me repeat again. If there is no edge, this is a leaf of some tree. If there is no edge using this vertex, then we can delete this vertex. And I'm still satisfying all these properties to be required for to be a minor model, right? Because if I delete a leaf, connected subgraph still stays connected, right? Tree become connected. Tree is still connected even if I delete the leaf. Yeah. But I mean, I was worried about the single case where you only have one vertex, but H is no isolated vertex. Yeah. Right, what happens if H is isolated vertex? Okay, so then, yeah, so that's that's one case. Or 5e has only one vertex. And V is isolated in H. That's an exceptional case, right? Now, the reason is because otherwise we replace 5v by 5v delete w. And this is still connected. The reason why it's connected is because 5v now has at least 2 vertices, and when you delete a leaf from the tree, you have a connected graph. All right, now that's the assumption. Now what does that mean? That means since the maximum degree of H is at most 3, 5v has at most 3 leaves. So it's a tree with at most 3 leaves. And tree with at most 3 leaves all look like this graph, right? There's no other option. I mean, this is 3 leaves. I mean, you might have 2 leaves or 1. No, there's no case with the 1 leaf. We call the leaf to be a vertex of degree 1, but you may have a case like this. Oh, so actually, yeah, so I don't have to worry about this, because if I have a vertex of degree 1, that means tree must have at least 2 vertices, so nothing to worry. All right, so each of 5 looks like one of these 3 types, and the outside world, the edges outside, will be connected like this. There are only, remember that V has only 3 incident edges, and the images of these 3 incident edges may look like this, or maybe it may look like this, or it may look like that, right? The reason why I know that there is an edge joining to a leaf is because of this assumption, which we can apply. So then what does the graph look like? You can pick this vertex and that vertex and that vertex, and then blue vertices will be the branch vertices for the topological minor. So now we end up seeing that we obtained a subdivision of H as a subgraph of G. Right? What edges do we use? We use edges like by taking edges in union of all vertices of H. You take a union of edges of the tree, and for all edges of H, you give a, okay, so I mean, for that one, I can just say phi of EH, right? If you collect all these edges and vertex edges, then you have this connected subgraphs. No, I don't say connected. I don't know whether H is connected, but you have a graph, I mean subgraph of G, which is subdivision of H. And we use the fact that the maximum degree is at most 3 crucially, because if you have a tree with at most 3 leaves, then it looks like one of these 3 types. So that's the crucial thing. All right, so that's the converse of this property between topological minors and minors. Now, finally, let's talk about Euler tours. Okay, so many of the graph theory books says that the origin of graph theory is due to Euler, who shows that there is no way to traverse every bridge in a city called Königsberg. Do you remember the island? There was an island, and then bridges like this. And the question was, can you go through every bridge exactly once? Okay, let me try. Can you go and instead come back to initial locations? Oops, right, something like this. And so that's it's commonly called as the origin of graph theory, because Euler was the first one who proved that this is impossible in this particular case. And it was not the Euler who proved that this is if and only if thing. So later, it was only many years later that someone else proved that actually that's if and only if thing. Right, so let me say it as follows. A circuit is Eulerian. So remember, a circuit is a closed walk without repeated edges. A circuit is Eulerian if it contains every edge. And a graph is Eulerian if it has an Eulerian circuit. Right, so then we can classify the graphs having Eulerian circuit. So a graph G has an Eulerian circuit if and only if G is connected and every vertex has even degree. Am I doing all right? No, actually not quite. There's a catch. So let me move a little bit. So graph is connected but after deleting isolated vertices. Because isolated vertices, so the vertex of degree 0 doesn't do anything for Eulerian circuit, so I don't care. And graph may still have an Eulerian circuit even though it has an isolated vertex. So if I just say the graph is connected, then it's false, because you might have a graph with isolated vertex which is disconnected but having an Eulerian circuit. Right? So how do we prove that? How about the forward direction? Well, if it's Eulerian circuit, so let's first assume that graph has no isolated vertex, because they don't do anything for Eulerian circuit. We assume that G has no isolated vertex. And isolated vertices have degree 0, they are still even, so don't worry. I mean, nothing to worry. And now, why is it connected? If I have a vertex, 2 vertices, E and V to W, and now there's no isolated vertex, so every vertex has an edge instant. So let's say E and F. And then Eulerian circuit exists, so this Eulerian circuit will become, so the part of the Eulerian circuit is a walk from V to W, because it uses E and it uses F. So therefore, there's a path. Right. And why does it have even degree? Because right, if I look at the Eulerian circuit, each vertex, if you follow the Eulerian circuit, so V0, E1, V1, E2, V2, EK, VK, where VK is equal to V0. Now look at the time, like V. Let's say this is some vertex V, and V appears somewhere. Like here's, oops. Here's a V, here's a V, here's a V. What can happen? Now there's an edge incoming, there's an edge outgoing, right? So edge incoming, outgoing, incoming, outgoing. So for V, if you come in by EI, then you go out by EI plus 1. And you can pair them, right? So whenever you have an edge incoming, then you must have an edge outgoing. And those edges are not repeated almost. Right? So whenever you have incoming edges, you have outgoing edges. So the number of edges is going to be equal to twice number of incoming edges. Number of edges is instant with B. So this is even. Now, this is almost correct, except one little thing. Right? What happens if you have a loop? If you have a loop, what happens? Well, actually, when you have a loop, let's say, for instance, EI plus 1 could be a loop, then it go out and come back, right? And here, I was counting loops twice, because when you come in, you go out, and when you come in, you go out, right? So each loop is counted twice, right? Because it's counted as one outgoing edge, and it's counted as one incoming edge. And remember that when we define the degree of the vertex, right? Where was it? When we define the degree of the vertex, we made sure that loops are counted twice. Yes. Right? Loops are counted twice. So when you take a degree, loops are counted twice, so it doesn't matter. It's the same thing. So this is another reason why we would prefer defining degree as that. Okay. Now that's all it was. So no, but still we haven't proved the converse, right? So so far we proved that if you have an Eulerian circuit, then graph is connected at the leading isolated vertices, and every vertex has even degree. How about the converse? If you want to prove the converse, I think it's easier to use induction. So let's try to use induction on the set of number of edges of the graph G. How do we do the induction? All right. What kind of things should we do? Now, if G has no edges, then we are done. Oh, Okay, that's another place. If graph has no edges, then it must have Eulerian. No, I cannot say the graph has Eulerian circuit because there is no circuit. Right, empty set is not a circuit. Can I say it's a closed work? Okay, let me go back. So, well, how do we define a circuit? I think that's the right. And when we define a circuit, we have to say that circuit must have at least one edges. Okay, circuit should have a length at least one, because otherwise every graph will have a circuit, and we don't want to say that. All right, we don't want to say that every graph is a circuit. When you define cycle, we made sure that k is at least one, so it has to use at least one. Now, how do we fix the statement here? So if we have no edges, then graph still has Eulerian circuit. No, graph doesn't have Eulerian circuit. So let's say set of edges is empty. Okay, so this is a fix, right? So graph has an Eulerian circuit or has an empty edge set. The edge set is empty if and only if graph is connected, and after deleting isolate vertices, and every vertex has even degree. So then it's trivial. All right. Now, then what I mean is, if you have no edges, then graph the statement trivially holds. Now, how about the other case? So if G okay, so we may assume that the set of edges is non-empty. Now, that means I must have a vertex of degree non-zero. Right? Because there is an edge, so therefore you must have a vertex of degree at least one. But every vertex has degree even. So that means G has a component having no vertex of degree 1 or 0. Right? Let's take a component having at least one edge, and that component has no vertex of degree 1 because by the assumption there's no even degree vertex. So therefore this component has no vertex of degree 1 or 0. And that means it's not a tree. Because every tree with at least two vertices have degree 1 vertex. And so there's a cycle. So G has a cycle. Right? So I must have cycle. Now let's delete these edges of cycle. So I have a cycle and delete it. What happens? Well, I might have disconnected the graph. Okay, let me. Right, so this is component 1, 2, 3, 4. There are many components, and but each component, what we can say is that each component of G delete EC is Eulerian by the induction hypothesis. Why? Because if you look at each component, every vertex is even degree because you delete the blue edges. I mean, you delete the cycle C, so you either decrease degree by 2 or 0. So what used to be even degree vertex will still become even degree vertex. And as long as graph stays connected, we can apply induction hypothesis. And I know that component is connected, so by applying induction hypothesis, each component will have Eulerian circuit. Now, what's left is just to combine these Eulerian circuit. Right, so what we do is follow this cycle C, and as soon as we reach new component, we follow the Eulerian circuit of that component, and then continue. And as soon as we reach new component, we follow Eulerian circuit of that component, and continue. And Eulerian circuit, and continue, Eulerian circuit, continue. So let me just write this way. We combine, we traverse edges of graph G by traversing C and using Eulerian circuits of each component of G delete E of C, right? And that is the Eulerian circuit of the whole graph. Okay, so that's the, and how do I know, how do I know that there is no component okay, every component, every okay, let me fix here, every non-trivial. By I mean having at least one edge, right? If I have a component with no edges, then I don't care. It does not have a Eulerian circuit, but maybe it's better. Now I realized, it could have been better if I define Eulerian graph as a graph having every vertex even degree, but okay, let me define this way. No, is it good? Okay, so right, so we say graph is Eulerian. Okay, let me later, for the later purpose, let me fix here. Graph is Eulerian if every vertex has even degree. So now, I mean, you see the motivation why we would like to say the even degree, and now this is a bit cleaner. But in the theorem, I didn't say the graph is Eulerian. I just said the graph has Eulerian circuit, right? Yeah, so that's what it means to be Eulerian. Yes. Right, so every non-trivial component of G delete EC has an Eulerian circuit, therefore we can traverse all of them. Alright, so that's it for the basics. In the next lecture, we'll talk about matchings in the bipartite graph. Okay, thanks for watching.